Smith, and in this Pluralsight on-demand video, we're going to take a look at the Dependency Inversion principle, the D in the solid principles of object-oriented design. The Dependency Inversion principle is one of the most important principles of building object-oriented software, and we're actually going to have to split this module into two parts because there's quite a lot to cover. We're going to start off by defining the Dependency Inversion principle. We'll outline some of the issues that occur in software that does not follow this principle. We'll further demonstrate that with an example in which we'll see how these problems arise. Then we'll analyze that problem, figure out a way to refactor it in order to apply this principle, and then we'll have a look at some related fundamentals that apply as well along the way. So the Dependency Inversion principle states that high-level modules should not depend on low-level modules. Both should depend on abstractions. Furthermore, abstractions should not depend on details, but rather details should depend on abstractions. This is from the Agile Principles, Patterns, and Practices in C# book by Robert C. Martin and Micah Martin. So, if you've been following along on these modules thus far, you know that I like these motivational posters that demonstrate these principles. This one is for the Dependency Inversion principle and says, would you solder a lamp directly to the electrical wiring in a wall? As you can see with our electric gadgets, we have a common interface, which is our plug, which if you're in the US looks like the one shown in the upper right here. And using this common interface, we're able to plug in any number of different devices that implement that interface. That's what Dependency Inversion allows us to do as well. When we write our classes in such a way that their dependencies are exposed as interfaces, we are then able to pass in implementations of those interfaces just as we're able to plug in any particular device we want into the wall socket. So before we go any further talking about Dependency Inversion, we should consider what exactly are dependencies. Obviously, if you're writing .NET software, you have taken a dependency on the .NET platform, the .NET framework, more or less on Windows, unless you're developing for Mono. This is something that is not, within the scope of dependency inversion per se. It's a dependency that you're probably pretty comfortable with and that you don't expect to change too much with the course of your software. However, the dependencies we're talking about with regard to our application design are more low level and things that we are going to expect to possibly change as part of our application during its lifetime. For example, access to third-party libraries. These can often be things that will change frequently, and therefore, if possible, we want to be able to inject alternate implementations of these third-party libraries into our code. Thus, we're certain that our choice of third-party libraries is not likely to change for the lifetime of our application. Certainly our database represents a dependency, assuming that our application has one, and it's definitely one of the things that you will want to wrap in such a way that it is not an implicit dependency within your code, but rather something that can be injected and replaced. We'll see more about how to do that soon. Other dependencies are less obvious. For example, if your code references the file system, if it uses email, if it sends email, or even checks email from a pop-in box, for example, if it uses web services, or really any kind of network access at all, would be a dependency as well. Any sort of system resources, even things like just the clock we might access via datetime.now, represent further dependencies that might require you to invert in the case of situations where they affect the behavior of your application and there's no way for you to test it unless you run it at certain times of day. Configuration can be a dependency in terms of the files that you use for configuring your application. The new keyword is itself a possible indication that you've got a dependency within your application. You want to limit places in which you allow your application to instantiate new objects, unless they're primitives like strings, for example. And related to that is the use of static methods. Anytime you're calling a static method, you're adding a dependency to your code that cannot easily be separated from the calling code in the case of trying to run a test for it, or in the case of wanting to change your code, the way your code works throughout the entire application in one place. If you have static methods sprinkled throughout your code, it's very difficult to change them all through one configuration change or one startup file change. Sleep can also be a dependency, as well as the use of random. It can be very difficult to test code that is supposed to give you random results. So if you specify an interface that you use for generating your random values, then for test you can override that interface and say, well, if the random value is this, then I should expect this result. And similarly, it allows you to more easily test so-called random data. These are some of the dependencies that you should be aware of. It's certainly not an exhaustive list, but I think I've covered most of the major ones that you'll typically find in a .NET business application. Most traditional programming works in such a way that dependencies naturally accrue within the code because the higher level modules tend to call the low level modules, and by calling them, they also tend to instantiate them as they need them. So it's very typical for you to have, for instance, a user interface application that references some business logic, and it might new up one of those business logic classes, perhaps a customer class or an order class, and do some work with it. And in the course of calling the methods on that class, maybe it has to talk to the database, or maybe it has to talk to some other sort of infrastructure. Typically, that business logic class would then new up a data access component or a logger component or some other kind of class to do its work. And so ultimately, the user interface is depending on the business logic. The business logic is depending on the infrastructure and utility and data access classes. Furthermore, it's often the case that a facade layer is implemented using static methods in order to facilitate a simpler API for those business level methods. It's much simpler for the business logic method to be able to call save customer on a data access layer static method than for it to implement 20 lines of ADO.NET code itself. So these can also represent dependencies that can be very tricky to extract out of your application. And then finally, it's typical that class instantiation and call stack logic is scattered throughout the application. This violates the single responsibility principle because now every class that is deciding who its collaborators are through the use of static methods or the new keyword to instantiate specific instances with which it wants to work is now responsible not just for its actual work, but also for determining who it's working with. And these are actually separate responsibilities that the single responsibility principle should dictate that you would want to put into separate classes. When we're talking about class dependencies, we want to be honest. That means that our class constructor should require any dependencies that the class actually needs. Classes whose constructors make this very clear have what I would call explicit dependencies. However, classes that do not make this clear have implicit or hidden dependencies. They're lying to you when they say that you can just new them up without passing them anything, but they don't work if the database isn't there. That's telling you something that is false. It's telling you that this class would work, but then it's not letting you know about the fact that, oh, by the way, I actually need a database in order to do anything. So for example, here's a class called Hello World Hidden that has a hidden dependency on the system clock. And so it'll work a certain way in the morning, and another way in the afternoon, and another way in the evening, but there's no way for you to alter that dependency. In this case, it's violating the open and close principle in that if you wanted to change the logic for the dates or the times of day when it does its thing, or if you wanted to be able to test it in some way that lets you run all three paths through the method without having to run your tests at different times of day, you would have a hard time doing so. So classes should instead declare what it is that they need. For instance, with the Hello World example, we need a date time in order for us to determine which greeting to pass back. We could pass in date time through the constructor, or if we want to and it was only being used for one method, we could pass it into the method itself. If we don't want to pass in a particular value object like a date time, we could pass in an interface that knows how to return date times, such as an iCalendar that perhaps implements the now method. And then we could write an implementation of the iCalendar interface that use the system.datetime.now implementation by default. But then when we were writing our tests, we could use whatever implementation of that we wanted. And we could have an afternoon iCalendar that always returned 2 p.m., for example. And we could use that in our test to verify that we received good afternoon whenever we passed in the afternoon calendar implementation. Let's look at a simple demo showing how violating the dependency inversion principle can cause problems in your application. In this example, we're going to look at a simple e-commerce application, which includes an order class that represents the customer's order. And the order class has a checkout method, which takes in a shopping cart. The shopping cart has some items in it that the user is purchasing. We have some payment details that will have values such as credit card or cash. And we have an option for whether or not we want to notify the customer when their order has checked out. If we look at the logic for this, we can see that when we have a credit card payment type, we're going to charge the card. In any event, we're going to reserve some inventory. And if the customer has requested it, we will notify the customer. As it stands here, we see that there are no explicit dependencies being set in the constructor for the order class, nor are there any implicit dependencies in this method that would be shown with a static method call or a new instance of a particular implementation. However, when we start to drill down into these methods that it's calling, for instance, notify customer, you can see that we do in fact have dependencies on mail message and SMTP client, datetime.now, which is a static method, as well as a logger static method for this error method here that they're using for error handling. Similarly, the inventory reservation method uses an inventory system that instantiates, and charge card likewise uses a new payment gateway. So the dependencies in this class include the payment gateway, the inventory system, the SMTP client and mail message classes, the logger, as well as datetime.now. We'll be able to find a lot of these dependencies using the architecture generate dependency graph by class menu item in Visual Studio 2010, assuming you have the correct version. And if you do that, you'll get something that looks similar to this, which will show you all the class level dependencies. It won't show you the static methods. So you'll see here that we're depending on payment details, card, logger, order item, etc. The only static method it's not showing is the datetime.now. Our logger method isn't shown here. In fact, it's not going to show you anything that's in the framework. It's only going to show you classes that are defined within your project with the settings that I've used. So what's the problem here? The issue is that if we want to try and test the order class, it's going to be difficult to inject some of these classes that it requires. If we look at our test class, we have 2 tests written so far. We've named our class order checkout should, and that lets us use sort of a sentence structure when we say these tests. So we can say order checkout should not fail with no items, no notification, no credit card. So we set up with a new order, a new cart, payment details of cash, and we set the notify customer to false. When we run this, we don't have any real indication of success or failure except for the fact that we assume that if we have an exception, it must have worked, because our method is a void method. And so we can run this one test, and it does in fact pass when we have nothing to do and no items to do it with. The next one is that we don't want it to fail when we have no items, but we do have notification, and we still have no credit card. So at this point, we've set a customer email to this bogus someone@nowhere.com, and we specify should notify customer to true. When we run this test, however, we get an exception because I'm running this on my development machine and I don't actually have an SMTP server running. So if we view this test results, we'll see that it was a system net web exception, unable to connect to the remote server, and it was unable to make a connection to port 25 of localhost when it tried to send the message. And if we look at the stack trace, you'll see this is all SMTP client trying to send this mail message. So at that point, I'm pretty much stuck. I've got 2 options. I can come into my cart should method and I can start doing things like creating a fake SMTP message. I can go into my order and I can say something like, if I'm in test mode, don't actually send my message. There's various hacks I can do to try and get around this. There's even a handy tool that you maybe want to use sometime called SMTP for Dev that you can use. You can download this from CodePlex actually, and it'll sit there and listen on port 25 on your dev machine. And then if you go and run tests like this one, you'll see it flashes and it shows you the message that you received. So here's my order details, for instance. If you completely shut it down, minimize it, and rerun your test, it'll pop up a little post message here that shows you that a message was received. So this will still let you test your emails with this particular thing. And similarly, if this were a database access, I could write some kind of a test database that I could use. If this were talking to my payment gateway supports some kind of fake credentials that I can pass it that'll give me back some kind of data. There's all kinds of ways that I can do some sort of integration test that really does use the implementation that I expect to use in production. But having to put together and glue together all this infrastructure, just to be able to test the logic of my order, be able to say that, really I just want to know that when notified customer is true, that this notified customer method is called. I don't care about the details of it. I don't care if it's notifying them with an email or an SMS text, or if somebody's running down the hall to let them know that their cart have been processed. I just care that when that flag is set, this method is called. And right now, because of the tight coupling of the order class to these dependencies, the mail message and the SMTP client, I have no way of testing that. And that's causing me a lot of pain when I want to be able to write some tests to show that this is really doing what I expect it to do. The problem with our order class is that it has a lot of hidden dependencies. It's depending on mail message, SMTP client, the inventory system, the payment gateway, a logger, and datetime.now. And the result is that we have a class that has very tight coupling. There's no easy way to change any of the implementation details, so this is an open-closed principle violation. The only way we can change how order works is to go in and actually change its code. And it all ends up being very difficult to test. So let's talk about a particular technique that we can use to make this easier. Dependency injection is a technique that's used to allow calling code to inject the dependencies that a class needs when it is instantiated. This also goes by the term of the Hollywood principle, which is basically, don't call us, we'll call you. So instead of our class calling SMTP client, it could say that it needs some kind of notification service that knows how to do notification, and it will go ahead and call that, but it doesn't need to instantiate itself. Now the term dependency injection, or DI, has three primary techniques that I want to talk about here. The first one is constructor injection, the second is property injection, or setter injection, and the third one is parameter injection. There are other methods that exist both for dependency injection as well as to solve the general problem of the dependencies that exist when a class knows about the things that it's newing up. One of those is called service location, but those are beyond the scope of this particular module. So the first type of dependency injection is called constructor ejection. This is an instance of the strategy pattern, which is a very popular design pattern. It's extremely useful in object-oriented programming. With constructor injection, dependencies are passed in via the constructor. The constructor then is being honest with the things that call it, in that it is explicitly stating the things that it needs in order for it to be in a valid state and to be able to do the work that it expects to be able to do. The pros of this approach are that classes self-document what they need. It works well with or without a container, and I'll talk more about containers in a moment. And classes are always in a valid state once constructed. Some of the cons are that constructors can end up with a great many parameters if they have a lot of dependencies, which is a design smell in and of itself that needs to be addressed. Also, some features, for example, serialization, may require a default constructor, for example, a parameterless constructor. So even though you may have a constructor that explicitly specifies all of the things that your class depends on, for reasons like need to use serialization, you may also still have to expose a parameterless constructor that doesn't have those things set up. Also, some methods in the class may not require things that other methods require. So placing those dependencies into the constructor effectively makes all of the methods require all of the dependencies. This is also a design smell because if you have methods in your class that don't require certain things and other methods that do, it's likely telling you that your class lacks cohesion, and it would be wise for you to refactor it into multiple classes that share dependencies and share common tasks. Another type of injection is property injection, which is also known as setter injection because you set the thing that you're injecting using the set method on the property. Some of the pros are that the dependency can be changed at any time during the object lifetime, and thus this is very flexible. However, one of the cons is that objects are in an invalid state between construction and the setting of dependencies via setters, unless the constructor calls setters. And it also can be less intuitive because there isn't any one place that you can go on that class, short of reading the documentation, that tells you exactly the properties that need to be set and perhaps the order of setting those properties in order for the class to ultimately be usable by the client calling code. And then the third method is through parameter injection. In this case, the dependencies are simply passed in as parameters to the method. This is the most granular and it's very flexible. It does not require any changes to the rest of the class. However, some of the cons are that this breaks the method's signature. So if you have a method that's already in use by a great many classes in your application, some of which perhaps you cannot easily change, then breaking that method signature could be very expensive. Whereas adding another constructor that allows you to pass in this dependency might be something that you can easily do without breaking any of the existing code that depends on that method. Similar to with constructor injection, this can result in having many parameters on your method. But again, this is a design smell in and of itself and something that you should address in order to create a more cohesive design. You should consider using parameter injection primarily if you only have one method in a particular class that has a certain dependency. Otherwise, it's better, in my opinion, to use constructor injection because this is able to make it very explicit to anyone using your code what exactly it needs in order to function. When we refactor our example class, the things that we're going to do in order to apply the dependency inversion principle are to extract the dependencies out into interfaces and then inject implementations of these interfaces into the order. As a side thing, we'll also reduce the order's responsibilities by applying the single responsibility principle, but we're going to just gloss over that as that's a separate module in and of itself. Let's look back at our solution, our order object. The order object has a number of dependencies that we need to extract. And we're going to do this by applying the strategy pattern and using something called Constructor Injection. So in order to do Constructor Injection, the first thing we need a constructor. We'll add that. And we can take some of the things that are common throughout the entire class that are currently parameters on checkout and move these into our constructor parameters as well. So for instance, we could say our order requires a cart. And then we can turn that into a field that we can use elsewhere. Likewise, we could say that we always have to have payment details. So we'll add those as well. And make that a field too. And the next thing we do is take some of our dependencies and convert those into interfaces that we can inject. So the first one that we see here is notify customer. And so we can simply take this exact signature and make that our interface. So we're going to say we have a void notified customer. We'll come up here and we'll just create a new interface in the same class for now. We'll call it I notify customer for now. And you see it takes a cart in order to do its work. If we look at this, we're going to see that the cart has the customer email. and pretty much it looks like everything else it needs is here. Now the notify customer implementation might need to kick in an iLogger or something at some point, but for now we can do what we need with just a simple interface, I think. So once we have this interface, let's go ahead and create a derived type for it, and we'll just do this right here, and we'll call this a notify customer service. And of course we want to implement the members. And so we have a notified customer, and we really just want to take this whole method out of here and place it into here. And at that point we have this notified customer service that we can use. If we come back into our constructor, we can then pass in our notified customer and pass that in as well. And now it's just a matter of wiring up these fields so that they are using the fields instead. So if we come in here and change notify customer to be underscore notify customer dot, now that's going to go ahead and call our notify customer method on our interface, and we eliminated the dependency within order on anything having to do with SMTP. Now we'll see in a moment how we can repeat this same process in order to pull out the dependency on the inventory system and the dependency on our charge card. So let's look at our class dependencies as they began with our order class. And you can see that the order class had strong dependencies on the payment details, the payment gateway, the inventory system. There's also, not shown here, dependency on the system.net classes that are doing SMTP stuff. Now I've gone ahead and done all the refactoring already inside of the loose coupling folder here. You can download this code and go through this yourself. The online order is something that currently does the work of everything that you would expect for an online version of the order that needs to do notification as well as credit card processing and inventory reservation. In the single responsibility principle video, we looked at a couple of other alternatives to order. For instance, it was in a point of sale order, you might not need to do a notification service because the customer is standing there and they know they made their purchase. But in this case, we're talking about online orders. We identified these 4 fields that we wanted to pass, in addition to cart, which is being passed in on the base class of order through its constructor. And finally, with each of these interfaces established, we also created default implementation. So the notification service looks like the one that I just showed you, and there's also a payment processor and a reservation service that are simply cut and pasted out of what was there previously. So looking at online order, we can see that the entire class is now only 36 lines of code, and it's very easy to follow. You can also see that the new keyword does not exist anywhere in here. This class now takes in all of its dependencies through its constructor, making it very easy for us to test the class through the use of fake implementations. So let's look at what the tests would look like. So look at our first test here, where we want to send the total amount to the credit card processor. We want to verify that whatever the cart amount is actually what we're going to charge the user's credit card. So for this, we're going to create fake implementations of each of our dependencies. We have a fake payment processor, fake reservation service, fake notification service. We have a cart with $5.05 in it. That's our payment type credit card. We create our order and check out. Once we check out, we want to check 2 things. We want to verify, first of all, that our payment processor was called at all, and then we want to verify that our payment processor had the correct amount passed into it. We're going to compare that with the cart total amount. Now, our payment processor interface does not support what's called or amount passed. If we go look at iPayment processor, we'll see that the only method it supports is process credit card. So where are these coming from? Well, the nice thing about our fake implementation is that we can do anything we want with it. So within our fake payment processor, we don't actually process any credit cards, but we do have a couple of fields that we want to be able to access. One of them called was called, one of them called amount passed. And using these, we're able to verify that this method was called and that the amount passed is one that we expected. If we were interested in verifying payment details, we could expose those here as well, and then check for them in our test. Remember that the point of unit tests is not to verify that the full system works, or to test whether or not the payment processor itself works. The point of the unit test on order.checkout, which is the method that we're testing, is to verify that checkout does what we expect it to do. What do we expect checkout to do in this case? Well, we want it to process the credit card with the correct amount. We want it to call our reservation service, and we want to call our notification service. We want to know that it does these things, and perhaps that it does them under certain conditions and in a certain order, if necessary. And that's it. We don't want to have to test every little piece of the system just to test this one method. And that's what separating out the dependencies is allowing us to do, is to isolate the order.checkout method and be able to test just the content of this method without having to have actual implementations of all of its dependencies. If we look back at one of the original methods tests we had a test here that said that it should not fail with no items, no credit card, but it should have notification. And if we run this, we see that we get this exact same behavior that we did before. Now let's look at the class dependencies on online order and compare them with what we had with order. We've broken away from having dependencies on many of the concrete classes that order had and replaced those with interfaces. So we now have dependencies on 3 interfaces: reservation, payment, and notification, as well as dependencies on still payment details, the cart, and the order. But those we're able to do without any kind of external infrastructure requirements like web services, database, SMTP servers, etc. And so this still allows us to test our online order without having to use any of those extraneous bits of infrastructure. So just to review, the main change that we made is we went into online order, we identified the dependencies that it had and created interfaces for those dependencies. We modeled those interfaces based on simply what this particular class needs. So the client is the one that dictated what these interfaces should be. And then we moved the implementation details that previously existed in this class into implementations of those interfaces. And this was pretty much just a straight cut and paste of the method that we had previously on order. We moved into now a notification service, who currently has just one responsibility of sending this message to a customer. This makes this particular class very easy to test and very easy to follow because it's doing only one thing. And it cleans up our online order class considerably as well, so that it's much easier to follow and simpler too. The next thing about this is that online order is now being very explicit about its dependencies. You know when you create an online order that you must have a cart, a payment details, a payment processor, a reservation service, and a notification service. If you don't have those things, you simply cannot create an online order. There's no default constructor for it. And so we are able to tell clients of the online order class exactly what dependencies it needs in order to function. Now let's take a look at some design styles related to the dependency inversion principle. The first one is simplest. It's simply use of the new keyword. If you find in your code you're using the new keyword and moving up actual instantiations of particular instances of classes rather than interfaces, it's often a sign that you could apply the dependency inversion principle. In this case, what we're showing you is this new inventory system. This is something that if it has extra dependencies, maybe it's talking to a database, now the code around it has inherited that dependency. So the only way for you to keep this for each loop from having to deal with whatever the dependencies the inventory system carries along with it is to replace that with an abstraction. And the simplest way to do so is to replace it with an interface that we use and then simply inject the interface using the strategy pattern and constructor injection. Similar to the use of the new keyword is the use of static methods or properties. This can be something as simple as a datetime.now that's crept into your code. Instead of having an actual datetime passed in or an abstraction such as an iCalendar or an datetime interface that supports the now method you want to be able to pass in. Another very common scenario is the use of static method to create sort of a facade layer for your data access. And so you'll see this frequently where you have something that offers a bunch of different methods like save customer or validate customer or things like that, which are static. And unfortunately, if you have a method that does a bunch of stuff and then ends with data access.save customer, and that static method talks directly to ADO.net and talks directly to the database, there's now no way to eliminate the dependency on the database. Just the same if that static method is talking to a file system or any other dependency. So the best thing is to avoid static methods because of the fact that they cause these kinds of problems with inherited dependencies. And one place where you should use or could use static methods is when they don't actually touch anything other than the parameters that are passed into them. For example, if you have a static method that added two numbers together and took in those numbers as parameters, there will be no problem with that because it's not going to cause any sort of a dependency problem. But if you have a static method that instantiates other classes, and those classes might have dependencies of their own, now that's something that is going to likely cause you problems when it comes time to test. If we're not instantiating our objects, where do we instantiate them? Somewhere we have to do this. So typically what happens when you apply dependency injection is you get many small interfaces, which is good because each one of them is very cohesive, they're loosely coupled to one another, they follow the signal responsibility principle, they follow the interface segregation principle, but at some point you have to actually create these objects. There's a couple of different choices for this. The first one is you can create a default constructor that then inherits from your constructor that actually takes in the interfaces and provides a default implementation of each of those interfaces. So in the example that we showed, we had an online order that took an iNotification service as one of the parameters in the constructor. We could create a default constructor that automatically passes in a new notification service, which is our default implementation of the iNotification service. Now any code that is calling this will continue to work just as it did before, and we'll still be able to inject alternate implementations, for instance, in our tests, when we wish to do so. This is sometimes called poor man's dependency injection or poor man's IOC. IOC means version of control, and we'll see that in just a moment. The other option is to manually instantiate everything in your application startup routine or main method. In a web app, this could be an application start in global NSX. And another option is to use IOC container, which does the same thing, typically in the main or startup method, but it has a bunch of features that it supports so that you can wire these things up in an intelligent fashion and go to one place and see how your object graph is going to be set up for your application. So IOC containers, or inversion of control containers, are responsible for object graph instantiation. They're initiated when the application begins, and typically they either use code or configuration, such as an XML to determine what is going to be set up to be used whenever an interface is called for. Managed interfaces and implementations to be used are registered with the container. So for instance, you might have in your container something that says you want to register iNotification service and say that anywhere I see an object that requires a notification service, I want to use a new instance with a notification service. Dependencies on these interfaces are then resolved either in application startup or at runtime. You can call an IOC resolve method that will go and find whatever the instance is that's mapped to that interface at runtime, or you can have a container that automatically is able to create the dependency graph for a given class by using its constructor. Typically, the constructor that has the most parameters is the one that we'll use. So in the example with our online order, we could have an IOC container create one of those for us, and it would automatically supply the types that were needed for the iPayment processor, the iReservation service, and the iNotification service. Sometimes it's necessary to create a factory class that is able to create your class for you and then register the factory class and its dependencies with the IOC container. IOC containers are a fairly large topic in and of themselves. There are quite a few of them available, most of which are completely free. Some of those are listed here, including Microsoft Unity, Structure Map, Inject, Windsor, and Funk or Monk, just to name a few. So to summarize, you should depend on abstractions rather than concrete type whenever possible. You want to avoid forcing your high-level modules to depend on low-level modules through direct instantiation or through static method or property calls. You want to declare your class dependencies explicitly in their constructors wherever possible. You can inject dependencies through such constructors or alternatively through the property or through a parameter injection. Some of the fundamentals that are related to this topic include SRP, ISP, the facade pattern, and inversion of control containers, as well as the strategy pattern that we discussed. I recommend the Agile Principles, Patterns, and Practices book listed here, as well as Martin Fowler's article on Dependency Injection, which is at the URL shown right here. I need to provide credits for the one motivational picker I used for the dependency inversion principle that is shown here. And with that, thank you very much. This has been part one of a principle of object-oriented design software fundamentals dependency inversion principle. We're going to have another second part to this that's going to show you how you can apply this principle at the application level and at the solution and project level in your Visual Studio projects. Thanks. Hi, this is Steve Smith, and this Pluralsight